Hi, good evening, all of you. After 2 weeks, ne? 3 weeks? I can't remember. So this is our atomic structure homework sheet 1 online discussion session 2. Discussion session, yes, part 2. Ne? Part 1 we completed that Friday. Today we are going to complete the other part. And again, then this is parallel to our physical classes. We are doing at Farade, Kandy and Farade Kottala. And plus online also. We met last Sunday. You mean that classes? No? Yeah. I mean the online. Sorry. Then some of student been send me messages that they are having classes at the same time today, maths class, combined maths class. But since I plan it, I'm doing that one today because they can watch recording. And yeah, some people then don't like to come to live classes and they want to watch the recording. Recording mean, then I upload that to the YouTube channel and then only we share that link. It may take several days. You have to wait for that one. So always I recommend, although it's published there, but this is only for few sessions, right? I don't plan to upload all the discussion session to the YouTube channel, only for few. After that, definitely you have to participate the live discussion sessions. Otherwise, you will miss it, unfortunately. Okay, right. Let's start it. Ne? Today, what we have actually mainly the past paper questions discussions. I hope all of you have tried it. To develop the confidence, we tried several questions we did and discussed. To test the confidence, to test your confidence, we move to examiner's viewpoint. That means past paper questions. I have given, I think, since 2003 to 2024 past paper question related to that section we covered so far. Not so far. In the first 4 notes, I think, up to the Broglie Wavelength, right? Even last week I shared. What I shared the homework sheet 2 also. In the physical classes, I distributed it. All of you got it, I think. Homework sheet 2. Yes. Now you have to start them. You have to start them and then you have to complete them. Because most probably not the next Friday, the following Friday, I will do the first part of that second homework sheet discussion. Therefore, before that, you have to try all the questions and then collect the doubts and everything. Okay, shall we go to the discussion? Yes, good. I hope you are having the tute with you. We are going to start from this section, 2024, A-level 2024 question. Thereafter, we continue the others. I'm not going to share this one because I hope all of you have the hard copy with you. It's compulsory, but I don't have a hard copy. That's the question. Anyway, I use this one. Sorry, what's in A-level 2024? De Broglie wavelength of two particles X and Y. That ratio is given. The values are given 1 nanometer, 3 nanometer respective. X and Y particles. Ne? If the masses of X is 3 times the mass of Y, ratio of kinetic energies of X and Y, de Broglie wavelength, masses, kinetic energies. Then what's the proper equation you are going to use for this one? In the theory class, I gave you 3 equations for this. Lambda equals H over P, lambda equals H over mv, lambda equals H over root 2 mv. That's what I gave you. According to the data and the questions given, you are given wave length, you are given masses, you are given kinetic energies. So which one is the suitable one? Definitely the third one. Eh? Third one is the suitable one. Then we apply that one to the first particle. So what's the first particle? X. To X we apply this equation. I'm talking about third one. Eh? There lambda X means it's 1 nanometer is equal to, let's keep it in SI unit, nano replaced by -9 meter. H is constant because we are going to get the ratio. Since we are going to get the ratio, better you have a plan before you do this one. Better you have a plan. My plan is this one. We did this question at the class. Did they? It's okay. Then some people may miss it. It's okay. I'm doing briefly. Yeah? We did it. It's okay. We just did briefly. So since it's a ratio, I'm not going to substitute these things because those are constant value and definitely they are cancelled out. Then H, I keep it like that. Then 2 also cancelled out. But what about the mass of X? Mass of X given, if the mass of X is 3 times the mass of Y, I take the mass of Y, M, then this is 3 times, means 3M. And kinetic energy ratio is the question. Let's keep it like EX. Then I do that one for the Y particle also. Then Y wavelength is 3 nanometer, nano mean -9 meter. And H here, square root 2. But I took 3M, then this should be definitely M. Because mass of this 3 times of this. Sorry. Kinetic energy of Y particle, I take it like EY. Thereafter, what I need the ratio EX EY. But I need EX EY. You see, it is H over EX, H over EY. If I just divide first one by second one, what do we get? 1 over EX divided by 1 over EY. Then when you take upside down multiplication, it's EY over EX. But I need EX over EY. They ask X is to Y. To get the X is to Y, better I divide that one by second one by first. These are kind of then easy ways to get the answers. Second one by third one mean it's 3 over 1. Everything cancel, meter cancel, -9 cancel. Second one mean H over root 2M EY multiplied by, this becomes upside down, H here root 2 into 3M EX. That's what we have. But HH cancelled out. We can get that from everything into one. So it becomes 2 3M EX over 2 times M EY. That's what we have. So what happened? 2 cancel. Cancel. We get root part here. I'm not, okay with that one. So therefore, to remove the root part, you know what to do. We take the square root of both sides. So I take it like that. 3 over 1 square. And this is root. What do we have? 3 EX over EY. But here also I take the square. Then now you know what to do. In this case, it becomes then 9 over 1. But that's equal to 3 times EX over EY. But 3 and 9 again cancelled out. Finally, we end up with 3 is to 1. That's CX over EY. 3 is to 1. Where do you find it? 3 is to 1. It's in fourth answer. What's the question? It's the question one mean the 2024 question. Elevate 2024 question. So answer is fourth one. Answer is fourth. 3 is to 1. Got it? Ready? That is 2024 question. Since we did even in the classroom, so we don't have to worry about that. Let's move to A-level 2023. But before that, I need space. I have to erase this one. So I hope all of you got it. Or shall I share the screenshot? Sorry, I shared the screenshot, so you have it. A-level 2023 question. One question given from this. As you can see, each and every year it's given. This part is important to collect marks. Maybe 1 mark MCQ, but 1 plus 1, 2. If the wavelength of radiation used in a microwave urn is 1.1 centimeter, the energy of 1 photon of this microwave is, you know, these are very, very simple. These are past paper question. But we did quite advanced question even in the theory class. You remember that one? So therefore, those who tried those type of question find very easy this type of question. So energy of one photon, it's Hc over lambda, because wavelength given lambda, the relationship between energy and wavelength is equals Hc over lambda. And we know, I told you this E refers then energy of one photon, one quantum energy packet. So H 6.63, 10 to the power of minus 34 joule second. This is 3 10 to the power of 8 meter per second. As you can see, the constants are given. It is 6.6. We don't need even 6.63. Can you see that one? In class, we use 6.63. The exact value is 6.626. But here within the bracket, it's given just 6.6. Use them, right? Use the given values. 6.6, 10 to the power of minus 34. C not given, but it's okay. We take 3 10 to the power of minus 8. But normally these C constant, those things are listed out in the first page of MCQ paper. You can find them. Lambda, what about lambda? 1.1, but centimeter. But we substitute that one in SI unit, meter. Centi can be replaced with minus 2. Generally, in most of the case, you have that one in nanometer or maybe picometer. Nano mean 10 to the power of minus 9, pico mean 10 to the power of minus 12. But it is here given as centi, 10 to the power of minus 2. If that is the case, then how do we find it out? The values. Then simplify this. Meter cancel, per second cancel. We end up with joule. I advise you to first simplify the units and get your final unit. And then I ask you to check that one with the relevance of that one with the question. Question is to find the energy, and I end up with joule, then I am happy. Because joule for energy, yeah, acceptable. Then we simplify the 10 to the powers. Then 10 to the power of minus 2 cancel with this minus 32. 10 to the power of 8 cancel with this minus 24. 10 to the power of minus 24. That's what we end up with. But once I simplify this, you know, a 1.1, 6.6, it's exactly 6. 6 into 3, it's 18. 18, 10 to the power of minus 24. In other words, 1.8, 10 to the power of minus 24 joule. That's what I have. But I don't know whether it's given in joule or kilojoule. It's given in joule. 1.8, 10 to the power of minus 23. Wait. Because 18 minus 24 mean 1.8, it minus 23. So your answer is then third one. So anyone has doubt, you can tell me. Third answer, the power should be, yeah, 10 to the power of minus 24. Simple compared to the questions we discussed in our class. 2023 discussed, then we have 2021. 2021 question is, there is no any calculation. They ask these statements. Select the correct statement with regard to particles associated with cathode rays. Do you remember cathode ray experiment? Yes. What's the particle in cathode ray? It's the electron. Negative particle, it's the electron. They ask about these things. We discuss properties of cathode rays. You remember how many properties? 11 properties we discuss under theory class. Using that knowledge, we can answer this type of question. First one, particles are uncharged. No, negative. Second, they travel from anode to cathode. No, you remember that the paddle wheel rotates according to the direction of rotation. We can easily conclude the direction of cathode rays. It's from cathode to anode, not anode to cathode. Their charge to mass ratio depends on the nature of the gas and the pressure inside the cathode ray tube. Their charge to mass ratio. I told you cathode ray particle is electron. It has a certain charge, E. It has a certain mass, M. Then we take charge to mass ratio of this cathode ray particle. It's actually the charge to mass ratio of the electron. Then that day I told you, if the gas discharge tube is filled with helium gas, it undergoes ionization. Once the electrons collide with this one, electrons emitted from the cathode, now fast moving electrons, once it collides with the helium atom or gas, then it undergoes ionization, releasing electron. So this is the electron of helium atom. What about the charge of that electron? Definitely E. What about the mass of electron? Definitely M. Right? Then let's say you use then hydrogen gas. Then hydrogen also undergo ionization. Then this electron is electron from hydrogen. Then what about the charges of these two? Will be different or same? Electron of hydrogen, electron of helium, charges are same. What about the masses of these things? Same or different? Masses are same. Then what about the charge to mass ratio? Definitely same. So the charge to mass ratio of cathode rays, I told you, doesn't depend on the type of gas, doesn't depend on the type of material in the cathode ray, right? Doesn't depend on even pressure. All right. Next, third one. Then fourth one, the direction of travel is affected by, of course, since it's negatively charged particle, when it passes through the electric field, you know the deflection. Definitely, it moves towards the positively charged plate. So that one is correct. Fourth one. Then 2021, the answer should be fourth one. Very easily we can decide it. Okay, we did properties, many properties. According to that, we can decide it easy. Yes, fourth one is the correct answer. Right. That's 2021, only one MCQ. And let's move to 2022, A-level 2022. Sorry, 2020. Eh? A-level 2020. That's very straightforward question. I mean, if you remember those people and the discoveries, definitely you can answer. I think in the class I asked you to do that activity. I hope you remember. Did I say that one? I mean, I asked you to prepare this short note. In that case, it's a table. First column, you have the name of the person. You can start from even Democritus, Empedocles, Plato and Aristotle, John Dalton. So likewise, you can list out all the names of the person who are responsible, who are important in the case of this history part, discovery of these subatomic particles, determination of charge, mass, those things, right? And other experiments like gold foil experiments, radioactivity part. So then list out the names of scientists, and then here write the importance of this. This maybe it's a discovery, maybe they have given a model, maybe they have found a certain value like charge of electron by R. Billiken. Then important. When you have this summary, very easily you can answer this type of question. So what about the first one? Positive rays inside the cathode ray tube. Positive ray actually by E Goldstein means eigen maybe 205. Next one, radioactivity, not Robert Millikan, it's definitely Henry Becquerel. Then it should be simply E Goldstein and Henry Becquerel. Fifth answer, A-level 20, the answer should be 5. You don't have to spend time there. Within few seconds, you can find it out. There is another 2020 question. It's again based on the de Broglie partner. Let's see how to do that one. I first share this one. Since these are quite easy one, I take it quite fast. Here, you know that one, I'm not explaining the theories. I'm explaining how to get the answer for the given question. Theories we did in theory class. There is another 2020 question. It's about again the calculation part regarding the Broglie wavelength. A-level 2020. De Broglie wavelength of a neutron traveling with velocity is given lambda. It's a neutron. Wavelength is given lambda. If the kinetic energy of this neutron is increased 4 times, the new de Broglie wave, then this is same particle. In the previous case, 2 particles, X and Y. This is same particle, neutron. But what we do actually, we change the kinetic energy of this one. They ask about, again, the wavelength. Then de Broglie wavelength and kinetic energy mean definitely third equation should be used. Lambda equals h over root 2me. Right? Then to first time, we apply neutron to the first instance. Wavelength is, let's say, lambda. Lambda is given, okay? H. Since I'm going to get the ratio again, I don't substitute the values because it's cancelled. And neutron mean, both case it's neutron mean, mass should be constant. Then I keep it like M. But what's kinetic energy? First I take E, first time. Thereafter, we increase that one to 4 times. Then let's say new lambda is lambda dash or something. H constant, 2 constant, mass also constant, because both case it's neutron, and kinetic energy it's 4 times it's increased. But I need lambda dash, therefore I divide second one by first one, then lambda dash over lambda. Lambda dash over lambda, that's easy for me, that's why I do second over 2. Right? But second, h over root 2me, 2m4e. And this is multiplication upside down, 2me. Then HH cancelled out easily. We get root part here. I can take everything to root 2me divided by 2m4e. Then that's again cancel, 2 cancel, m cancel, e cancel. This is, I take it here. Lambda dash over lambda is equal to 1 over root 4. So what's that? It's 1 over 2. So if I subject lambda dash, it will be half times lambda, means lambda over 2. First answer should be lambda over 2. Once you then increase the kinetic energy of a certain particle by 4 times, your new wavelength will be half of the initial wavelength. That's what we get through this calculation. This is A-level 2020 question. First answer. Yes, first answer, correct. Let's move to 2019. It's again regarding the scientists' names, discoveries, those parts. Do that activity, you will be okay with these things. Consider the energy absorbed or released by atom is quantized. Quantized means that like energy packets. It's not continuous. That means any amount of energy will not be released during an electron transition. Any amount of energy will not be absorbed during electron transition. There is a certain value or whole number multiple of that value will be released or absorbed during electron transition. That's the meaning of quantization of energy. We discussed that one in detail within the class. Then who said this idea? You remember that idea? One is actually even Albert Einstein. He said some idea about what the word photon. But before that, Max Planck. Max Planck gave that idea like quantum. He said one simple, the smallest value it can carry the energy, maybe quantum. That's how we introduce. But photon, that word was given by another scientist, Albert Einstein. So therefore, it should be Max Planck's. Then Max Planck's is found in second answer and third answer. Therefore, it could be second or third. But small particle under appropriate conditions show wave property. Particle has wave property. It's definitely Louis de Broglie. Louis de Broglie is given in second answer. So therefore, this should be second answer. But there is another question. If you carefully look at that, which one? Yeah, fourth answer, Niels Bohr and Louis de Broglie. First part is okay, second part is okay, but we have question regarding second part. What did you learn in Bohr theory? I think you remember that one. During electron transition, I said energy is absorbed if electron jumps from lower energy to high energy level. Energy is released if electron transmit from high energy level to low energy level. That's what I said. But I said I gave another equation. Do you remember that? This energy absorbed or released is given n times h mu. That's what I said. This was there in Bohr theory. So what's the meaning of this? H mu? H mu represent one quantum or one photon. Then n is what? The number of photon. The integer, maybe 1, 2, 3, 10 like that. This means 1 h mu, 2 h mu, 3 h mu. There is no 2.5 h mu. Then again, within the Bohr theory also, there is some idea about the quantization of energy. Because this is the one small energy packet. During electron transition, it can release maybe 5 energy packets. It's not any amount of energy. It's selected value. So therefore, even in the Bohr theory, we have some idea about the quantization of energy. Therefore, in the marking scheme, actually, they have given even fourth one as the answer. Therefore, it can be 2, it can be 4. Both are accepted. Both are accepted here. 2 or 4 can be answer for 2019 question. I hope you're okay with this one. Any doubt you have, let me know. After 2019, what we have 2017. So what about that? It's again that scientist and the discovery part. The scientists who, it should be who, then W only, HO missing, who disproved Thomson's plum pudding model. You remember that timeline I draw when I explain the theory? I take 2017 timeline. To draw timeline, actually, I need some space. But, then first I get 350 BC. So what is that? It's the Empedocles idea. Democritus, Aristotle, Plato. Those are the people important here. Thereafter, I got 1808. Who is that? 1808. 1808, it's then Dalton's atomic theory. That's what I said. Dalton introduced the atom like simply a rigid goal, like golf ball. After that, in 1897, I think, 1897, J.J. Thomson gave the plum pudding model. In that case, the atom is positively charged sphere in which the negatively charged electrons are embedded in it, like plums in a pudding. Then in 1911, I think, I can't remember exactly the number. We don't need these years and everything. 1911, we have nuclear model. In the nuclear model, what we have, all the positive values are concentrated into one small area that's called nucleus. Outside the nucleus, we get electron. That was Rutherford idea. Then the question is, who disproved Thomson? Thomson said positive charge can be found everywhere within the nucleus, but Rutherford said, no, it can't be. What did Rutherford say? Positive charges can be found only in the small area at the core of this one. It's called nucleus. So therefore, who disproved plum pudding model? Definitely Ernst Rutherford, because of the nuclear discovery of the nucleus. Look at Ernst Rutherford is found in first answer. Therefore, 2017, the first question is first answer. Right? We continue this pattern for the others also, but here we don't need it. Got it? So it should be first. There is another question in 2017, but it's a calculation part. 2017, it's a calculation part. I hope you find this is quite challenging. Was that challenging, the question? You found it like quite easy or difficult? Yes, kind of. I did in my past, but I got the answer. Yeah, good. Yeah, then compared to the other question, quite challenging. A lamp produces 6 joule energy per second. Right? 1 second, then it produces 6 joules. That is one important information. But this is then energy. Energy means electromagnetic radiation. If it is electromagnetic radiation, there should be frequency and wavelength. It's given in blue-green, blue region. Then blue light is electromagnetic radiation. But wavelength is given 470 nanometer. 6 joule, but it's 470 nanometer wavelength photon. Thereafter, for how long should the lamp be lit to generate this number of photons? Okay, they asked the time for not the energy, but the number of photons, 110 to the power of 20 photons. Correct? To generate this number of photons through the lamp, what will be the time we should lit that like that bulb, the lamp? That was the question. So how to connect all this information? Right? If you carefully look at this one, then wavelength is given. From the wavelength, you can find out the energy of one photon. Energy of one photon. But then 6 joule released in 1 second. Then since you know the energy of one photon, you can find out then how many photons are available within 6 joule. This doesn't mean that 474 6 joule, right? It's given 1 second, this total energy released. It doesn't mean that one photon. One photon has wavelength this. We don't know how many photons are there. We can easily calculate because through E equals hc over lambda, you can find the energy of one photon. If you divide 6 joule by that energy, you can find number of photon released per second. Then per second, you know the number of photons. Then for this number of photon, you can find out simply the time. That's the way we do. But in this case, actually, then in MCQ, yeah, we'll come to the answer. Yeah. Hari? In this case, in MCQs, we don't have time to simplify this one step by step. Remember that one. In MCQ, better you take the final expression for the final answer. I take it in one step, but I don't know whether you can understand it. Step by step, I'll show you. Thereafter, I'll show you the easy method. E equals hc over lambda. So what do we calculate? We calculate energy of one photon minus 34 joules second. Forget that one. This is where you get energy of one photon. Energy of one photon. But per second, then how many energy they released? They released 6 joule. Then I can calculate the number of photon released. Number of photon released per second. So how do we get it? It's this way. It released per second 6 joule, but per photon you have this much energy. Then if I want to calculate how many photons available within that 6 joule, you can divide the total energy by the energy released by one photon minus 34, 310 to the power of 8 divided by 470, 10 to the power of minus 9. That's also joule. Then joule cancelled out because it's a number of photon. There cannot be any unit. That is for 1 second, this number of photon. But they ask what's the time for this number of photon. Then how do we get it? We write the expression like this. Then we can say the time. That's your question. It's this way. Right? This number of photon per second. Then I write it like this. Right? This number of photon. I write the whole expression. I told you not to simplify them. I take this one just to this side. Then you can understand it. Then 6 into 470, 10 to the power of minus 9 divided by 6.63, 10 to the power of minus 34 into 3, 10 to the power of 8. This is a number, no units, joule cancel. So this number of photon is for 1 second. Then for the given number of photon, 110 to the power of 20 photon. Once you simplify this, you finally end up with the time in second. Let's simplify this one now. We can take up this. This is upside down. Then definitely we can take it up. So we can rewrite it like 6.63, 10 to the power of minus 34, 10 to the power of 8 divided by 6, 470, 10 to the power of minus 9 multiplied by 110 to the power of 20. That is where we get the final expression. It's the same thing as I explained the first time. So what is it? We calculate the energy of one photon. You know, energy of one photon is this part. We divide that energy of one photon by the total energy. It gives the number of photon per second. Then once you multiply that one by the given number of photon, you get the total time. So that is how we finally end up with here second. Let's now simplify it. Now it is quite easy. 10 to the power of plus 8 plus 20, it's plus 28. 28 minus 34, it's minus 6. Yes. Then 10 to the power of minus 6 cancel with this minus 9. Then minus 3 remains. 10 to the power of minus 3 remains. Just leave it there. Then 3 and 6 cancel, it's 2. Right? Then 2 and nothing. Yes. No. You can keep 2. Then no option, then we have to simplify it. So once we simplify it, you can see actually this is 6.63. 472 means somewhere around 800, 914. Then 6.69, what do we get? 6.69, like 66 divided by 9. Like 66 divided by 9, what do we get? Like 7. 7. Right? What else we have? 10 to the power of minus 3, and this is, then it is plus 3. Yeah, you get exactly 7. It's cancelled out because 10 to the power of minus 3 up, it's plus 3. Plus 3 means it's like 6630 divided by, like 6,630 divided by 940. 6,630 divided by 940 means it's 7. This is 7 point something actually. Which one is the close answer for 7? Yes, we have 7.1, second answer. We get 7.1, second answer. Got it? So E equals hc over lambda, it's 1 photon. Then E total, this is per second I'm talking about. It's C divided by lambda times N. If you multiply the energy of 1 photon by the number of photon, you get the total energy. Then if you consider per second, E total is 6 joule. Then you have hc over lambda, h 6.63, 10 to the power of minus 34. This is 3, 10 to the power of 8. Number of photon is 6 joule. We don't know number of photon. That's what we are going to calculate. I'm going to calculate the number of photon per second. That's what I'm going to do. This is 470, 10 to the power of minus 9 meter. Forget the joule part. Joule also cancel. You end up with N, but there is no value. Got it? That's per second. Then I need how many times for that number of photon? So once you get this N subjected like 6, 470, 10 to the power of minus 9 divided by 6.63, 10 to the power of minus 34, 3, 10 to the power of 8. That's the number of photon per second. Now you are given the total number of photon. Then what can I do? Then what I do? I divide the number of photon by the number of photon released per second. Then you get finally the time for this number of photon. That's what we have finally. 110 to the power of 20. 110 to the power of 20 divided by this number. Yes, we have this number. So that way, even we can find the answer. That's what we did. I hope you understood it. Anyone has any doubt, let me know. If you don't get it, let me know. I can explain it again. All right. Silence mean no any doubt. You get it. Okay. 2017, it's quite not like the usual question. They have given it in a different manner. 2016 also, I think we did that question also in the class. I remember it's the first question I gave as a past paper question. Green light of wavelength 4.42, 10 to the power of minus 9. Minus 7 observed emission spectrum, the energy of 1 photon again. Since I'm talking about 2016, since lambda given and question energy of photon, yes, we apply this equation again. Then 6.63, 10 to the power of minus 34 joule second, 3 10 to the power of 8 meter per second, divided by what's lambda value? It's 4.42, 10 to the power of minus 7 meter. Then simplify the unit, meter cancel, second per second cancel, we end up with joule. First simplify the unit, then you will get this very clear. Then simplify the 10 to the powers, minus 7, minus 27, plus 8, minus 19. So we end up with 10 to the power of minus 19 joule. Joule. Then we have quite a difficult number. You see 6.63 multiplied by 3 divided by 4.42. So in the class, I told you don't take this type of serious value as it is given. Better you simplify and get it like, forget 3 here. Take 6.6 multiplied by 3. What do we get? 6 into 6, 18, 1. 6 into 3 into 6, 18, 1. 3 into 6, 18, 1, 19. Since one decimal place I consider, it's 19.8 divided by 4.42. That's what we have. I roughly take it like 20 divided by 4. 10 to the power of minus 19 joule. So what do we get? 510 to the power of minus 19 joule. This is rough value. But when you carefully look at the answers, you have 4.5 to 1.5, 19.9. So yes, 19.9 is there, but it's divided by 4.42. It's not good then. Sorry, 1.5 can't be. 2 cannot be. Then it should be most probably 4.5. Correct? It's 4.5, 10 to the power of minus 19 joule. The exact value should be 4.5, 10 to the power of minus 19 joule. But when you go to the first answer, you see 4.5, 10 to the power of minus 19. The exact number is given, but the unit is given kilojoule. Can you see that one? So therefore, you have to be very, very careful when you select the proper answer, because it's the units are given like kilojoule. So be careful with this. Then can it be the first one? In most of MCQ, there are only 2 answers close by. Yes. Still, I cannot get it. Means the previous one. Previous one. I can't see your answer. Your answer Zoom username. May so better you ask that one through within the class also. In the class, I will explain it. Because only you ask that, others, I think, I mean, silence mean maybe they got it. Meet me after the class and then I will explain it again. This into this, divided by this. Okay, we get 4.5, 10 to the power of minus 19 joule. But the answers are given exact value 4.5, 10 to the power of minus 19. But in first answer, it's kilojoule. So it can't be first answer. Because we got it a joule, then we convert that into kilojoule. Once you divide that by 10 to the power of plus 3, it becomes 10 to the power of minus 3. 10 to the power of minus 3 minus 19, it's minus 22. So if you convert this into kilojoule, it's not minus 19, it's minus 22. Then that value is given in fourth answer. I know most of you forget the unit part and end up with this answer, 4.5, 10 to the power of minus 19. Then you have to be careful. Maybe you got that first answer and mark it, jump to the next one. So for 2016, the correct answer is fourth one. Correct answer is fourth one. Let's go to 2015. It's easy because direct answer is there. Plum pudding, J.J. Thompson. Anyone can answer that one if you remember this one. 15, plum pudding, it's J.J. Thompson means it's second answer. Let's move to 2014 question. 2014, the answer questions given ABCD type. I hope you know how to answer ABCD type. If it is ABCD type, you can't just select one and it is correct and you can't ignore the other and jump to the next one. In the previous cases like that, out of 5 answers, if you if you find the correct answer in the second place, no need to worry about the other 3. Then you can stop it and jump to the next one. In ABCD, it's not like that. You have to go to all these 4 statements and then find out whether it's given that one is correct or wrong. Right? Be careful with that one. Then after that, we answer it like that. First answer AB correct, second answer BC correct, Third answer, CD correct. Fourth answer, AD correct. Fifth answer, any other. Any other combination? No, there is no answer. All are incorrect or something, then definitely a fifth one. That's the way we answer. Okay, let's go to the statement one by one. First one, we are talking about electromagnetic radiation with 200 nanometer. Sorry, what we refer electromagnetic radiation with 200 nanometer. Now we go to statement A. Statement A is it has a higher frequency than the wavelength 400. Hari. In A, we compare that one with lambda 400. So what happened to lambda? It means this one, they refer 200 part. But here what happened from this to this, lambda increases. When lambda increases, or simply let's go from here to here because they refer this one, the statement given regarding this one. What is given 400, what is asked 200. So the lambda decreases. When lambda decreases, frequency should increase. Because frequency is inversely proportional to the wavelength. We have done that one in unit 1. So therefore, it means this one, this should have higher frequency. It has higher frequency. A is correct. Ne? It has a higher frequency than radiation of wavelength 400. Yes, it is in the visible region of electromagnetic spectrum. So what about the B part? Is it in visible region? Visible region, 400 to 700 nanometer. That's the boundaries I gave you. But this is 200. 200 is outside of this boundary. So it can't be then visible. Okay. The lambda is less than 400 means this has more energy than the visible region. So since it has more energy, maybe it is ultraviolet, maybe it is X-ray, we don't know, right? C statement, in a vacuum, it has a higher velocity than 400. But whatever the type given, maybe ultraviolet, maybe infrared, maybe microwave, whatever the electromagnetic radiation given, when you write the equation C equals mu lambda, the C value is constant. What is C value? It is the speed of this electromagnetic radiation. So whatever the type, the speed of this one is equal to speed of light. Maybe frequency different. Type difference mean definitely frequency different. Type difference mean definitely wavelength different. Then I said whatever the type. That means whatever the wavelength, whatever the frequency, the speed of this one is constant. It can't be greater or lower. Therefore, B wrong, C also wrong. Then what about the D part? D, its photon has a higher energy than photon of wavelength. Then here lambda given 200. No, 100. 100 nanometer. Right? This is the given value. It means we refer this one. Then once I go from given to this, it means this one, then lambda increases. When lambda increases, what happened to energy? Energy decreases. Lambda increases mean energy decreases. Therefore, it has lower energy compared to this one. Is it given low energy? Its photon has a higher energy than a photon of radiation of wavelength 100 nanometer. That is also wrong. Is that fine? Okay, visible, no. In a vacuum, higher velocity than this, no. Its photon has a higher energy than, no. Lambda increases mean photon energy decreases. Therefore, A only. A only mean it should be fifth answer. Can you repeat why C is incorrect again? What was the C statement? In a vacuum, it has a higher velocity than radiation of wavelength 400. Then what I ask you to compare the wavelength. What are the wavelength you have? You have 400 nanometer and you have 200 nanometer. Then wavelengths are different. Wavelengths are different. Then if I ask you to calculate the frequency of this, 200 nanometer. I ask you to calculate frequency of this. What's the equation you use? You use this one is C equals mu lambda. Since lambda is available, if I ask you to find out frequency, you use C equals mu lambda for this 200 nanometer. Then come to this one. Forget that one. Come to this. Lambda is given 400 nanometer. Then I ask you to calculate frequency for this wavelength. If I ask you to calculate the frequency for this wavelength, what is the equation you use then? Same equation. Since wavelength given, if I ask you to calculate frequency, then definitely you use C equals mu lambda. In both cases, we substitute C 310 to the power of 8. What's the meaning of that? Electromagnetic radiation with 200 nanometer travel with that speed, 310 to the power of 8. Electromagnetic radiation with 400 nanometer wavelength travel with that speed, 310 to the power of 8. Means both of these two have same speed. In that case, it says higher velocity that, no, it can't be. None of them is higher. Both of these two have same speed. So that is why C is wrong. So doesn't higher frequency mean higher velocity? No. Higher frequency mean not higher, the higher velocity, because I know your point. You look at this one, one with wavelength, this, what is it? 200 nanometer. Then 200, it's 400 in total. Other directly 400 wavelength like this. Other one wavelength is 400, means this distance 400. Then if I take this portion, this part, travel through certain point, you can get it. Ne? What's the frequency? Frequency is the number of waves that pass through a certain point in space per second. That's the frequency definition. So if I ask you to find out, then here, if this portion, if this part travel through that point per second, then there are two waves. There are two waves. Then what's the frequency of this? 2. 2 waves pass that through that point per second. 2 per second. Here, what about that? It's like 1 wavelength 400. It's not again. It's like 1. The frequency is 1 per second. Here 2 per second. Here 1 per second. Frequencies are different not because of the speed. Frequencies are different because of what? The wavelength. Shorter wavelength, you have many waves per given distance. The certain portion. If you consider certain portion of the electromagnetic radiation, you have more waves there. Longer wavelength means within that portion, you have very small number of waves. Did you get it? Because of the wavelength part, the frequency will change, not because of the speed. Got it, ne? Right. So likewise, then any doubt you have, better you ask it. I hope you are not then lazy to type and send it. Ne? I don't give the permission to unmute you. Then sometime you don't like to ask the question because you are lazy to type it. No, it's not then large number of words. You are lazy. Just like few words, ne? Maybe your time speed is very good. Speeder than mine one. But if I let you to speak, then oh my God, so many disturbances. 2014, there is another question, very, very easy. The neutron was discovered by 2014. The other question, neutron, James Chadwick, third answer. Anyone knows that one? Let's move to 2012. 2012, a big paragraph is given. But although a large paragraph is given, we don't need it. We need only the second small paragraph, 2 lines enough. Sometime in the past papers, they do like this. This is done mostly in the physics or something. when we get the physics MCQ, it's the information given is in a very large paragraph. Ne? In chemistry also, we have something like that. In old papers, we had that trick. Because if they have given a large paragraph, you have to read them. Once you read it, then definitely the time problem will be there. But finally, you can see only 2 or 3 lines important for us. Here, the information given, like when light strikes on certain metal surface, electrons can be ejected from it. Under photoelectric effect, we discuss it. Once the UV or whatever the type light irradiate to the metal plate, I gave you a nice diagram also. Then electrons will be ejected. Those electrons are received by certain receiver. And then we measure the current and everything. You remember that? That's what they have given. The energy carried by the photon in light is transferred to electrons in the metal. And if an electron acquires sufficient energy to overcome its attractive forces, I use the word that work function. You remember? With the positive charge nucleus, it may escape from the surface as a photoelectron. The minimum energy required for the electron to escape varies from one metal to the other. Yes, because metallic bond strength different, then definitely the work function will be different. We don't need those things. But the information given in the other 2 lines. The energy required for photoelectrons to be ejected from the surface of barium. Now the metal is barium. 240 kilojoules per mole of electron. Read it very carefully and get the information. It's for per mole. For 1 mole of electron, what's the total energy required? 240 kilojoules. For 1 mole of electron. Then tell me this one. We know this mole concept. Even we did that type of question. Tell me, in 1 mole of electrons, how many electrons are there? Not tell me, then type me. In 1 mole of electrons, then how many electrons are there? Then again, it is quite difficult. It's a huge number is there, and 10 to the powers also there. Then how to type it? I know your problem. Then I don't expect any answers. You, I think, know that one. The number is Avogadro's number, 6.63 10 to the power of, not 6.63, 6.022 10 to the power of 23 number of electron requires then 240 kilojoules. That's the meaning of this. 240 kilojoules is for this number of electron. Why I got it like this? Yes, Avogadro's constant. Because the next part is important. They ask this one, the minimum frequency, not energy, frequency of light capable of producing a photoelectron in barium is. Can you see that one? I think some of you didn't notice that one. They asked the minimum frequency. Right? Frequency of light capable of producing a photoelectron. One photoelectron they ask. The value is given for Avogadro's number of electrons, but the question is about 1 electron. That is why I show all these things very clearly. But first of all, without going to that frequency part, I try to calculate energy for 1 electron. Total energy for this number of electrons there, then for 1 electron. You know what to do? You divide this total energy by this number. Then you get energy per electron. For 1 electron, you get the energy equals what? It's 240 kilojoules divided by number of electrons available in mole. Ready? That's the energy. But the question is frequency. But you know what? Energy equals h mu. Then you can simply find out h mu. Then mu is the question. Now I get 240 kilojoule divided by 6.022 10 to the power of 23. That's divided by h. H is 6.63 10 to the power of minus 34 joule second. So that is how I get the substitution. So my question is this: is my substitution correct? I mean the unit wise. Did I do any mistake in substitution here? Can you see that? I did one mistake, ne? It is kilojoule. Here, kilojoule, here, joule. Can't be. It can't be. Joule should be cancelled out because frequency mean per second. Then say here, this only remain. Joule should be cancelled out. That's the point. I convert kilojoule into joule. How to convert kilojoule into joule? It's this. Then joule cancel. We get per second. That's the final thing. Now we are happy. Yeah, most of you got it. Harry, then let's simplify. 10 to the power of 3, 10 to the power of 23, 20. 10 to the power of plus 20 minus 34, it's minus 14. 10 to the power of minus 14 comes up, it becomes then plus 14. I write it here. 10 to the power of plus 14 per second. But what's the value? Value is something like 240 divided by 6.022 divided by 6.63. The numbers are quite difficult. 240, 6.022, 6.63. But in that case, again, follow my method. I mean, don't take 6.022. Forget 022. Take 6 only. Don't take 6.63. Then take just 6.6. There are 6 into 6, 36, 3. 6 into 6, 36, 3. It's then 39. It's 39.6. Again, 40. I can take 40. 39.40. Then 240 divided by 40. Then 0 cancel. 24 divided by, it's 6. 6 10 to the power of 14. 6 10 to the power of 14 per second. Now, go to the answers. Do we have 614? 614. Yes, exactly. We have fourth answer. We have fourth answer. 2014, first question, then fourth answer. Can you see that one? Do not take all these decimal places and then do simplification. It's then definitely a very bad idea. 2012, it's fourth answer. Thereafter, they ask the maximum wavelength of light that can produce this. Okay, then once frequency available, anyone can find wavelength. The wavelength equals C over mu. C I will 310 to the power of 8 meter per second. This is 610 to the power of 14 per second. The per second cancel. We end up with 4 and 14. It's then 6. Then this is half. Half mean 0.5. 0.5 10 to the power of minus 6 meter. Or in other words, 510 to the power of minus 7 meter. But they have given in nanometer. Oh my God. We end up with meter, then they give nanometer. Nano means what? 10 to the power of minus 9. Okay, then I write 10 to the power of minus 9. Then I can replace it with nano. But if I do 10 to the power of minus 9 here, I do mistake here. What's it? Then to remove that one, I take 500 10 to the power of minus 9. Is that clear? Because 500 can be written like 5 into 10 to the power of 2. This can be like 5 into 10 to the power of 2 into 10 to the power of minus 9 meter. It's okay because 10 to the power of plus 2, 10 to the power of minus 9, 10 to the power of minus 7. Yes, we have same value. 5 10 to the power of minus 7. But since I need minus 9 to replace with nano, I got it like that. It's got a 10 to the power of minus 9 can replace with nano. So it becomes 500 nanometer. Do we have 500 nanometer? Yes, third answer. Okay. So first question, fourth answer. Thereafter, second question, third answer. I hope you got it, this simplification part. Finally, we get 500 nanometer. Yeah, plus 3 should be. Then it should be third answer. Okay, that's about 2012. What do you think about these past paper questions? Can manage? Hmm? We did large number of questions even within the theory class. You know my method. I mean, we do small theory part, then that theory part is immediately followed with question. Once we do cover the theory part in that manner, that means definitely we are ready to answer any type of exam question. So therefore, I think you don't find any difficulty here. I hope you can manage. All of them can manage. Ne? Yes, can manage, manageable. Yes. Okay, good. Okay, let's move to the other part quickly. Today also I plan to do 2 hours class. Then now what's the time? 9:25 mean, okay, we got 1:25. Okay, the remaining part is enough to answer this question because these are quite simple one. Can manage. 2011 also we did in the class. Ne? Yeah, but I briefly explain that one. The reason is this comes in the recording means some people then were not in the class by that time. The quota, it's not then good to skip it. Ne? Some of them joined the class quite late, then they missed that part. So therefore, they watch the recording also. Therefore, this should go to the recording. So that's why I'm explaining. 2011, energy of 1 mole of photon with wavelength. Okay, again, wavelength given, question is energy. Then we apply this equation. But there is a problem because this is for 1 photon. You all know that one. But now, question is 1 mole of photon. Okay, then 1 mole of photon, I got it, this one. This multiplied by Avogadro's number, L, I use that one. Because 1 mole has Avogadro's number of photon. If 1 photon is this value, for Avogadro's number of photon, that value should be multiplied by that number. If I ask 2 photon, you know what to do. 1 photon, this value, if it is 2 photon, you multiply this by 2. Likewise. If it is 1 mole, it's Avogadro's number of photon. Then Avogadro's number, 6.63 minus 34 joule second, 3 10 to the power of 8 meter per second. This is 6.02 to 10 to the power of 23. Actually, there is a unit per mole. We learned that one calculation. I don't put it here. Lambda given 305. You see? They have given 305. They can easily give it like 300, but they have given 305. But do we care that one? No, we don't care. We just ignore 305. We take it like 300 and do simplification. But some people then take exact value and then take all these difficult numbers to the rough paper and put it there and simplify for the writing and simplifying. Definitely, they can't manage the time in that case. Through that method, they definitely face time management problem. So therefore, better you just ignore them. But first of all, you have to simplify this one. I mean, the unit meter, second per second, we end up with joule. Answer given in joule? No. Then again, notice that the answers are given in kilo. Thereafter, we take it like that. Okay, I multiply 6.6 by 6. What do we get? 6 into 6, 36, 3. 6 into 6, 39.6 divided by 305. But I take it like 40 divided by 300. 10 to the power of minus, wait a minute, minus 9 minus 25. In 23, 25, it's minus 2 remains. Am I correct? 8 is there. Oh my. I ignore 8 one. Then minus 2 into 8, what do we get? 10 to the power of 6 we get. 10 to the power of 6 we get. Because 8 also there. Minus 2 cancel with this, 6 there. 10 to the power of 6 is there. But I replace 10 to the power of 3 with kilo because I see all the answers are given in kilojoule. Therefore, I need kilojoule. Then out of 3, 10 to the power of 3, 10 to the power of 3 can be replaced with kilo. But out of 6, 3 replaced with this, then 3 remains. That is easy for me. Then this also cancelled out. It's something like 4,000. 4,000 divided by 30. 4,000 divided by 30, then 0 cancel. It's like 400 divided by 3. 400 divided by 3, and what do we get? Then there is 3 also. Wait a minute, there is another 3. Then very easy. 3, I miss it. 3 is there. 3 and 300 can be cancelled with 100. This 100 cancel with this one, then 10 to the power of 4. Then 10 to the power of 4 joule. 6.6 into 6, it's 39. 39 mean like 40. And then what is it? Like 400, 10 to the power of plus 3. Plus 3 can be replaced with kilojoule. It is easier than I thought. I mean, here I missed 3. These things then can, I mean, these are possible even in your exam. When you simplify, sometimes you miss one letter, then everything upside down, then you are stuck, then wasting time. So therefore, be careful. Here, I was not careful. That's the problem. Anyway, which one is the answer? Suitable answer. I got 400 kilojoule, but it's the rough value. Which one is close for that? 392 available. Third answer. So it's third answer. No need to get exact values and get it. You know that. 2011, there is another question, but there is no any calculation part there. 2011, it's given, but there is no calculation part. What is it? Which of the following statements are true regarding Rutherford Goldfoil experiment? First one, all the positive charges reside in a small region referred to as Goldfoil, of course. It's about the nucleus. The atom has a large empty space in which electrons move around the nucleus. Yes. Around the nucleus, electrons move. That is there in Rutherford field. Thomson's model of the atom was proved acceptable? No. It is disproved. It was disproved. Then we can cancel it. Electrons travel in fixed orbit. Did Rutherford say anything about the orbit and all stuff? No. He mentioned mainly the nucleus. Outside the nucleus, electrons are available. That's all. Then AB only. So 2011. AB only, according to that, it should be AB only mean second answer. 2011, there are 2 questions. It's third answer or fourth. Third answer for the first question, calculation part. Second answer for the other question. A true, B true, and C false. Yes, correct. All right. 2010, again, no any calculation part, but these things you have to be careful because several statements given. We have to be careful here. What's the first statement given? Which of the following statement? Not true. The other thing is that one. Sometimes they may ask true, sometimes they may ask correct, but sometimes they may ask not true, incorrect. That's the case. Electrons show both wave properties and particle properties. So we discussed that one under the cathode ray experiment. Electrons in an atom are dispersed in 3D region space around. Yes. Spherical shapes and all stuff. It's 3D, not 2D or not 1D. The neutron was detected when beryllium was bombarded with high energy alpha particle. Yes, that's the experiment done by Jane Chadwick. There was a thin beryllium sheet, then alpha particle bombarded there. The neutron is an uncharged particle with its mass approximately equal to that of proton. Yes, not exactly, but approximately they are equal. Those are directive theory part. Number of proton in an isotopes of an element are different from each other. Number of proton in isotope can't be. Actually, in isotope, which one is different? Protons are equal. Neutrons are different. 6, 7, 8. Protons are same. 6, 6, 6. That is incorrect. That is not true. Then 2010, answer should be 5. Very basic thing. But 2010, there is another question. Which of the following are true regarding the positive rays? Positive ray experiment. Now you go back to that one. True. This is ABC type. They are found together with cathode rays and responsible for the glow observed in region behind the perforated cathode. Exactly. You remember that. This was your gas discharge tube. This is the anode. Let's say this is anode, positive. This is the cathode, but it is perforate cathode. Perforate cathode means some holes. Once you apply the voltage, the usual cathode rays are generated. No issue. In addition to this, we observe red color glow behind the cathode. That was positive rays or canal rays or anode rays even. Still, we have cathode rays in the other side. Therefore, you see A is correct. A is true. They are formed, B, they are formed by loss of electrons from atoms, of course. When I explained the origin of these positive rays, I said these electrons, fast moving electrons, can collide with the gases inside this, and these gas particles can undergo ionization as a result of that. Because of ionization, electrons are generated and formed somewhere here, negative particle. That's then attracted, ions and positive particles, not electrons. Electrons there, these electrons are now attracted by the positive plate and cathode ray. But positive ions are there. These positive ions are attracted by the negative cathode. These particles go through that canals and generate positive wave. That is also correct. They are formed loss of, yes, be correct. What about C? They consist of particles whose mass is independent of the residue gas. No, it is definitely depends. Because I told you. Because if helium, the particle, positive particle is helium plus. You know, helium plus has how many? There are 2 protons, there are 2 neutrons, and even it has 1 electron. These are the particles available in helium plus ion. But if you use hydrogen gas, it ionizes and the positive particle is just H plus ion. So what about this? How many particles? Just 1 particle, only 1 electron. Then what about the mass of this particle and mass of this particle? Same? No, completely different. H plus ion, very light compared to helium plus ion. So this says independent of the residue gas. No, it depends. Therefore, it's wrong. Then what about D? D, they are not affected by electric no, of course they are affected because these are charged particles. These are still charged particle, positive charged particle. Then definitely they are affected by these fields. Therefore, D also wrong. And then once you go to that, A, B only correct. They are true statement. Which of the following are true statement? A, B only. A, B mean actually the first answer. Got it? In A, B, C, D, it takes some time. In A, B, C, D type, it takes some time. In your paper, from 31 to 40, 10 MCQs given, A, B, C, D type. That is quite a time-consuming part. Hari. That's about the 2011 and 2010. Let's move to 2009. Here, I directly go to the question discussions without discussing any other thing because I want to finish this within 2 hours. I hope still you are with me and not sleeping. Since you are physical students, then sometime online mean quite sleepy partner. Right. Now I move to 2009, but 2009 quite easy. It's about the name. What's the question? Following scientists identify who was not connected to the development of atomic theory. Then when we discuss the history, we mentioned several scientists, mainly about the models of the atom. Did I mention Bohr? Of course, Bohr theory, Bohr model. J.J. Thomson? Of course, Plum-Pudding model. Chadwick? Of course, discovery of neutron. Linus Pauling, then Phipps Rutherford, of course, nuclear model. But what about Linus Pauling? We didn't mention. I will mention the name of that person in the next week or the following week. Yes. Linus Pauling is important for electronegativity. Therefore, Linus Pauling is not connected to the development of these atomic theories. Therefore, it's fourth one. Next, 2007 given. In 2007, again, ABCD, they ask true statements. What are the true statements regarding what? Which of the following are true? Positive rays are formed when an electron is removed from an atom or molecule in a cathode ray tube. Yes, I just explained that. It undergoes ionization. Then ionization means removing electron. You get positive. That is attracted. That's positive rays. That is true. A true. 2007 then. A is true. What about B? Cathode rays originated from the cathode. Yes. That is where electrons are ejected. Then that is where the cathode rays are generated. Positive rays originate from the anode. What about that? No, it is not. You remember that one. For the positive rays, we say positive rays, anode rays, we say that one anode rays, but it doesn't mean that positive rays are generated at the anode. It's somewhere in between anode and cathode. Somewhere in between anode and cathode, but very close to the anode. But they say originated from the anode. That's completely wrong. It's not originated from the anode. D part, cathode rays are a type of electromagnetic radiation. Cathode ray, does it travel with the speed of light? What is your idea? Yeah, proton is generated middle of the gas. Not the middle. Maybe in the middle also some ions are there, but most of ions are generated, remember, close to the anode. That's why we name them as anode rays. Even the middle, yes, because some particle can be then can undergo ionization in the middle, but most of them close to the anode. But it's not at the anode. That's the point. Cathode rays are a type of electromagnetic radiation. Cathode rays means electrons. Electrons, cathode rays, and beta particle, beta ray. You remember in radioactivity, I said beta ray. When I give the note for alpha ray and beta ray, I compare the speeds. Alpha, beta, gamma, I compare the speeds, you remember. I said gamma, it's electromagnetic radiation, no particle nature, definitely no particle mean, no mass there. It has a particle nature, photon, that concept. No mass is there. Because of that, it travels with the speed of light, gamma ray, electromagnetic radiation. But once you go to beta, it's electron. Electron means there is a mass. Because of that, I said the speed of that one is 0.4 or 0.7 times the speed of light. You remember that one. That means it's not equal to speed of light because it has a certain mass. Then you see electromagnetic radiation, gamma doesn't have mass. Therefore, it can travel with speed of light. It's electromagnetic radiation. But once you come to beta ray, there is electron, it has a mass, it doesn't, then it is slower than gamma. So it can't be then electromagnetic radiation. It doesn't show the properties shown by electromagnetic radiation. One is that one, the speed part. So therefore, it says cathode rays are a type of electromagnetic radiation. No, it's cathode rays. What are cathode rays? Cathode ray is a beam of electron. It's not electromagnetic radiation, it's beam of electron. Therefore, D also wrong. Here, D also wrong. They ask a true statement, so it should be AB. AB means the answer is first one. 2007, answer should be first one. Did you get it? Anyone has any doubt regarding that? 2007 question. I hope you got it. 2006, which of the following statement incorrect regarding isotopes of an element? Isotopes of an element. They have, we know that one. You know, then once you go from 2024 to 2023, what about the standard, or what about the difficulty of the question? That is diluted, the standard diluted. Okay, which of the following statement incorrect? They have the same number of electrons. Yes. Same density. Incorrect, they ask. There is something in that question. Okay. This is the one, carbon 612, carbon 613, carbon 614. Number of protons same, number of electrons same, number of neutrons different. That's what I say. Then first question is, they ask incorrect, but first one correct. Number of electrons same. The same density. What about the density normally? Density is mass over volume. So if you consider unit volume of carbon 612, then mass is 12 here per unit volume. Assume like that. If you consider same unit volume of carbon 613, the mass is 13. If you consider same unit volume of carbon 14, the mass is 14. Then I consider the fixed volume, but masses are different. Masses increases from here to here. The mass increases mean definitely density increases. Density increases mean they can't have same density. Definitely they have different densities. That is the answer. They ask incorrect one. They have same density. No, it's wrong. Therefore, second one should be the answer for 2006. But what about the others then? Third one, similar chemical properties. Then remember, chemical property can be easily predicted based on electron configurations. Electron configuration is done according to number of protons, means the atomic number. We did that right in electron configuration. We wrote the electron configuration according to atomic number. Then atomic number equals, means number of proton equals, number of electron equal, then electron configuration equal, then the chemical properties are also equal. Mainly, we can predict the chemical properties mainly based on electron configuration. There are some other factors also. They have same chemical property, yes. Different number of neutrons, yes, 6, 7, 8. The same number of protons, yes, protons equal. So therefore, 2006, the answer should be second one. Same density can't be. 2005, it's ABCD type. We have to be careful. What about the first statement? Which of the following statement true? They ask true. Not wrong one, not incorrect. They ask true. Better you want. But these things are bolded in your paper. They say incorrect. That incorrect word is highlighted, bold. There's no need to highlight to underline. It's now given. True. Then electrons have particle as well as wave properties, of course. It's true. B. A proton is heavier than neutron. No. Neutron is heavier than proton. You remember the values I gave you. Roughly 1.67. Both case 1.67. But when you go to proton, 1.67, 26. Or 29, 26. 26, 10 to the power of minus 24 gram. But in the case of neutron, it's 1.6749. 10 to the power of minus 24 gram. Means neutron is slightly heavier than proton, not proton. It's wrong. All atoms have electrons, protons, and neutrons. All atoms have electron, proton, neutron. Is that true? No, it is not true. Why? Hydrogen, 1, 1. How many protons? 1. How many electrons? 1. How many neutrons? 0. 1 minus 1. It says all atoms. No, most of the atoms, but not all. Hydrogen is the exception. It's wrong there. All ions have at least one proton. All ions have at least one proton. Of course, it is correct. Ions are formed by removing electrons from the atom. All atoms have at least one proton. All atoms? Yes, all atoms have at least one proton. Because atomic numbers start from 1. Then definitely at least one proton. Then once you go to ions, in the case of hydrogen, we can make H plus ion. But once you go to the ion, do you remove protons? No. We remove electron. In this case, still one proton available, 0 electrons, 0 neutrons. But still proton available. Let's say someone make the H minus sign. That's also possible. But how did you make H minus sign? That's by adding electron. Got a number of proton? Yes, still one is there. Once you add one more electron, there are 2 electrons, but still no neutron. But still, you see, whatever the ion you consider, there must be at least one proton. Therefore, D also correct. Then AD correct. AD correct mean, if you remember that numbers I gave you, AD means it's fourth answer. 2005, it's fourth answer. Last one, A-level 2003. 2003, it's about which of the following statement true for this? For these are very, very simple one, but there is a mistake, printing mistake. It's 118 here. This is, I can't see that. 50 then. 50 and 118. Eh? They ask about number of electron proton, then very easy. Number of proton 50, number of electrons 50, number of neutrons is minus this, it is 8, 11, 5, 68. Those are the numbers. It has 50 electrons, yes. It has 50 protons, yes, to be correct. It has total number of 118 electrons and proton. No. 118 mass number. Mass number means number of proton and neutron, not electron. That's wrong. D, it has 68 neutrons. No. Yes, 68 neutrons available. A, B, D correct. In 2000, A correct, B correct, C wrong, D correct. Then 3 means any other. Got it? I think this discussion enough to understand those 20 years past, more than 20 years. I gave since 2003 to 2024 mean yes, more than 20 years papers. But there are some missing parts. Yes. So that's the explanation for past paper question. So if you can manage these type of question, then you don't have any problem regarding the section up to Broglie Wavelength. Homework sheet 2 given from that part to electron configuration part. So if you can do first do those other questions to develop the confidence, then you may do some mistakes and everything. Then through the discussion, you can overcome those things. Thereafter, the past paper questions. If you can manage those past paper questions, maybe 90% like that, then you're okay with that part. Until then, you have to keep studying, keep revising, keep doing questions, and then only you can develop the confidence up to that level. Got it? All right. Then I think this is enough. Anyone has any doubt? Next Friday, will the 1 week enough to have the first session? If it is enough, then yes, I can arrange next Friday. But there is a problem. I mean, some of combined maths people have in Friday class at this time. So then I want to shift this one to Thursday or Wednesday. I will discuss that in the class. Yeah, first I finish the first unit. Thereafter, we go to once we start unit 2 bonding, then I hope to start unit 3 also parallel. If you are okay, if you are ready for that one, then I will start 2 parallel units. And that one could be quite fast. I told you I will be very slow in the case of first unit and the second unit, but third unit I will do quite fast. You can understand still, right? Okay. Then that's enough for the day. Any other doubt? Yeah, parallel we will do that. Unit 2 and unit 3. Let's finish this unit 1 first. All right, then that's enough. Thanks. Thank you for, yeah, you wait until 10. No, it's not 10. 7 more minutes available. What do we do? Sing a song or something? All right, I plan to finish this part, then we finish it. Therefore, I'm going to stop this class. Good night. See you next day, Sunday, Tuesday. Bye-bye. Good night. Welcome. Welcome.